The producers and distributors of Tech AV welcome you to this introductory program on the subject of geared reduction units. During this program, you will be familiarized with the basic principles of gears, specifically their usage in performing speed reductions, which is vital to the operation of many industrial plants. So, let's begin as we first discuss the need for reduction and the basic principles involved. By taking even a quick look round most factories or production plants, you will no doubt notice just how many electric motors are used. Electric motors are the most usual source of power for most machinery, and in many plants the motors are of a fixed speed type, operating on three-phase alternating current. In order to produce useful torque or kilowatts of power, AC motors have to have relatively high spindle or shaft speeds, most often too high to be coupled directly to the machinery which they power. Between the motor and the machine, there is most usually a reduction device, which converts the AC motor's shaft speed to the desired speed required by the input shaft of the driven machine. The term reduction simply means a slowing down in revolutions per minute between a driver and a driven shaft. The term geared reduction means that the process of reduction is made via the use of gears of one kind or another. Other methods of reduction include drive belts and roller chains. Many processing operations are driven via a combination of methods, often through drive belts and then into a geared reduction unit. Here, the geared unit supplies a partial reduction between the power source and the driven machinery. Sometimes a reduction process is accomplished using open gears, as we see here. More commonly, you will see reduction units that are fully encased. We refer to these as closed reductions. There are various designs of gear types used to create reducers, and you will need to know how to identify each correctly. The simplest of gear designs is the spur gear. Spur gears are mostly used for small drives, including many domestic devices. A more usual industrial gear type, used extensively in reduction units, is the helical gear. The example shown is called a single helical. You can see, when compared to a spur-type gear, how the helical gear's teeth are offset at an angle. This feature offers greater strength and less noise in operation than spur gears. Larger reducers may include double helical gears. These gears offer great strength and, due to the opposing angles of the teeth, operate without side thrusts which do occur with single helical gears. Typically, reduction units are designed to provide compactness and simplicity. However, when the motor, reducer, and driven machinery are all set in a straight line, considerable space is often needed. To solve this problem, many users prefer to install an angle drive reduction, meaning that the input motion is diverted through the gear system to provide an angular change of direction, which is normally 90 degrees. Such a reducer is called a right-angle drive reduction. One method used to create an angle drive is through gears called bevel gears. A very popular angle drive, and one which you will see again in this series, is the worm and wheel type, often simply called worm drives. The action of the worm drive can be seen clearly here in this model. A screw thread, called the worm shaft, acts as the input. Motion via the screw action is transmitted into the worm gear. The output shaft, being the axis of the worm gear, provides the 90-degree change in the power flow direction. We have now looked at those gear types most usually encountered in reduction units. After the break, we'll be looking at how reduction processes are created. Welcome back as we continue in our geared reduction overview by discussing the process of reduction. In this simple demonstration, we have arranged two spur gears to illustrate the fact that by applying a turning force to one of the gears, we will cause movement or rotation in a second gear. Simple enough to follow. We'll now change the driven gear for one that has a greater number of teeth. To be specific, the large gear has 80 teeth and the driving gear has 50 teeth. We'll place marks here for visual reference. Now we'll rotate the driver by 1 revolution, and as you can see, the driven gear has yet to complete a revolution. The driver has to move approximately another 2/3 of a revolution to have the driven gear complete its full revolution. Let's assume that our drive gear is to be powered by an electric motor that has a rated shaft speed of 1,420 revolutions per minute. What will the driven gear's speed be in RPM? To calculate this, we first divide the number of teeth on the driven gear, 80, by the number of teeth on the driving gear, 50. This calculates to a figure of 1,6, and this we call the reduction factor. Now we divide the motor shaft speed, 1,420, by the reduction factor, which is 1,6, to obtain the driven gear speed. This calculates to 887,5, the speed in RPM of the driven gear. As an exercise, let's assume that we have a single-phase motor rated at 2,870 RPM. The input shaft speed of the machine it will drive must be no more than 1,500 RPM and no less than 1,400 RPM. What reduction factor will be necessary? Well, we simply divide the motor speed, 2,870, by the maximum desired input speed, 1,500, to arrive at 1,913, the ideal reduction factor. In reality, it is more likely that a reduction factor of 2 would be used, resulting in an input shaft speed of 1,435 RPM. In practice, reduction factors are normally expressed in ratios, and, in our example, we would simply say that the reduction unit required for our drive must have a ratio of 2:1. So far, we have seen that by altering the ratio between the number of teeth of a driver gear and that of a driven gear, we can achieve a speed reduction. The process has involved only 2 mating gears. We call this a single-stage reduction, or simply a single reduction. Far higher reductions can be achieved by using sets of gears in a number of stages. After the break, we'll look at various reduction methods and reducer types. Welcome back, as we now look at the types of reducers that you're likely to have to maintain. Many types and designs of reduction units are used throughout industry. The sizes, types, and reduction factors are all dependent upon the workload and application. In practice, you are most likely to encounter single, double, and triple reductions. A single reduction, as mentioned before, consists of 1 input gear, which we normally call a pinion, and 1 driven gear, often called the output gear. This terminology applies to spur, helical, or bevel gear types. A double reduction involves 2 stages of reduction. Typically, an input shaft carries a pinion. The pinion drives a first-stage reduction gear. This gear carries a second-stage pinion, which drives a final-stage output gear. In this manner, very high reduction factors can be built into a relatively small reduction unit. Triple reduction involves a further stage, whereby the second-stage driven gear carries a pinion that drives the final output gear. In this manner, it is possible to create quadruple, which is 4 stages of reduction, and even quintuple, 5 stages of reduction. The need for such high reduction factors becomes more critical where large mechanical devices are being driven and where output speeds are to be very low. Let's now look at some designs and types of reducers. In broad terms, there are 3 major reduction types, namely inline reducers, parallel shaft reducers, and angle drive reducers. An inline reducer has its input and output shafts in line, that is, on the same axis. This configuration is also known as concentric. A parallel shaft reducer is made in such a way that the input, intermediate, and output shafts all lie parallel to each other. In many examples, the input shaft may even be on the same side of the unit as the output. Such a configuration is also known as a transfer box. Angle drive reducers generally imply a 90-degree change of rotational direction between the input and output shafts. For this reason, this type is usually known as a right angle drive. The most commonly seen type is the worm and wheel unit, such as this popular Radicon. Another common angle drive reducer is the bevel pinion drive. Note that this type most usually continues its reduction through parallel shafts. Reducers are also described with their reduction factor, and this is given on each unit's specification plate. As we have already defined reduction, let's move on to the next descriptive term, namely size. Size is a little more difficult to explain owing to the different methods that are used by different manufacturers. Size may be given as the physical dimensions of the unit assembly, or, as is the norm with worm drives, size refers to the distance between the shaft centers. Some sizes are given in a unit's kilowatt capacity, usually referring to the rated output of the reducer when driven by the recommended motor. There are no set rules about how size is determined. Most often you will have to refer to the various gear manufacturers' data for this detail. The way in which a reducer is fixed or mounted into position is another descriptive term you should know about. The commonest mounting is a foot mount, whereby the unit is secured to a bed or base plate using bolts or set screws through pedestal brackets, generally called feet. The next example we see is called a shaft mount, which means that the reducer is supported by the input shaft of the driven machine. A support arm, or brace, prevents the reducer from revolving. Similar to a shaft mount type is the flange mount, so called because the reducer's body is supported by a flange that in turn is bolted to the framework of the plant. No support brace is necessary for flange-mounted reducers. In yet another configuration, we see an integral reducer, so called because the drive motor is an integral part of the reduction housing. In such types, the pinion is usually fixed directly to the motor shaft. By now, it will be obvious to you that a reducer can take on any size, shape, and design, and no doubt you will come across others. In this program, you have been introduced to the most widely used geared reduction units. In the following programs, we shall explain and demonstrate procedures involved when maintaining reducers. This brings us to the end of the overview program. When you have completed the exercise in your workbook, you may move on to any of the following programs in this series.